Okay, so if you haven't gotten your exam, come grab your exam. Um, the average before the curve was a 45, which was a little lower than not a lot lower than I thought, a little bit lower than I thought. And then as you can see on your exam, well, the scores in red on the back of the first page are just like the raw scores. And then the one in blue is the curved score. So the curve brought the average up to a 70 roughly. And so essentially I kept the highest score where it was, and then basically scrunched everybody up sort of together. I put the answers on Blackboard, and I also put a blank copy of the exam. So if you want to like for practice for the final, that's something that might be helpful to you. Any questions about like specific questions on the exam? Weird looking things. Oh, sorry.
I took just about 11, just about.
Ah, yes. Okay. That one, that's the hardest one. Um, so for that, I would, did you build a model? I'm not just asking you, but I'm asking everyone. Did you build a model of it? If you didn't, you should go back and build a model and try and get build a model of the first structure, and then see if you can rotate it around to fit the second structure. You should be able to do it. Additionally, if you look at, I have a copy of it. I think the main thing that makes it tricky is I flipped it upside down.
Yeah.
Yeah. So if you look at the first structure and then you rotate the exam 180 degrees and look at the second structure, I think they will look more similar if you do that. But I checked it like 5 times to make sure it was actually identical. Like because it doesn't look identical.
Yeah, I was like, I don't understand.
You're like, what is this? Yeah. What? 9 is the stereo centers, right? Okay. Let's do. Where is it? Here we go. Okay, so let's do this one. Okay, so the first thing to notice is this area over here, right? We've got a wedge and a hash, and you look at that and you go, ooh, stereo center, right? This was intentionally a little tricky and a little mean. So a methyl group is a CH3, right? So there's a CH3 at the end of the wedge. And then when we have a bond that just ends, the end of a line is always what? Methyl group, CH3. So these are two identical groups. And so this is not a stereocenter, all right? So if you assign something to it, it can't be correct because there's two identical groups on that carbon atom. The other stereocenters are there, and there. So when a group is not drawn, and of course the carbon's got to have 4 bonds, it's neutral, then that means the remaining group is a hydrogen. And so in both of these cases, there's no wedge explicitly drawn. And so coming toward us has to be hydrogen atoms. And then the stereocenter on the right, we have a wedge drawn but no hash. And so that means our hash is going to have a hydrogen on it. And so we can check to make sure that we've got 4 different groups. So I'm going to, okay, I'll call these A, B, and C, I guess. So for A, we've got a hydrogen, a sulfur, the stereocenter at the bottom, and then that carbonyl carbon at the top left. Okay, that's 4 different groups. For B, we've got the hydrogen, the oxygen, A, and the ring going clockwise. Okay, 4 different groups. And then on C, this one should be the easiest to tell that they're different. We've got a hydrogen, a methyl group, a sulfur, and an oxygen. Okay, so A, B, and C all have 4 different groups. Let's assign C first, again, because I think it's the easiest. So we need to sort everything based on size. And so the largest atom attached is sulfur, then then oxygen, then carbon, and then hydrogen. Hang on. Three, 4. Okay, so then we want to rotate everything so that hydrogen is at the back. Well, that's already the case here, so we're good. And now we look at clockwise versus counterclockwise. So 1, 2, 3, go like that. That's counterclockwise. And so that's S configuration for carbon C. Okay, for A, well, A and B both have the hydrogen coming forward, so we're going to have to deal with that in some way. So for A, well, the sulfur atom is going to be the highest priority because it's the heaviest. Then what next? Okay, well, A is attached to 2 different carbons, a carbonyl carbon and carbon B. Okay, so there's no difference in the element. And then next we have to look further out from those green carbons and see that, okay, B is attached to 1 oxygen, 1 carbon, and 1 hydrogen. And then the carbonyl carbon is attached twice to an oxygen and to a carbon. So that means that the carbonyl carbon is higher in priority than B related to A. And then, of course, the hydrogen is the lowest priority. Okay. So the hydrogen's coming toward us, which is not the way it's supposed to be. So that means when we look at 1, 2, and 3, they're going counterclockwise, but because the hydrogen is sort of in the wrong place, in this case, counterclockwise doesn't equal S, it equals R. Uh, Orange. Okay, and then for B, all right, well, B, the oxygen atom is going to be the highest priority. And then we've got 2 carbons attached to B, and those 2 carbons are A and this other carbon on the ring. So those are the same element, so we need to go a step further. A is attached to a sulfur. That's a large element, but the other orange carbon at the bottom isn't attached to any other element that's heavier than carbon. So A is going to take priority over that bottom carbon. Okay, so A is going to be, see, this gets kind of messy, doesn't it? A is 2, and then this carbon is 3, and then the hydrogen 4. All right, 1, 2, 3 counterclockwise. And the hydrogen is coming toward us. The lowest priority is coming toward us. And so that makes counterclockwise R. Does that feel a little bit better, maybe? All right, cool. Okay. So the Next chapter is on resonance structures. So you should have seen resonance structures at least a little bit in Gen Chem, hopefully. But we're going to look at them in a little bit more detail. A molecule that has a very important resonance structure is benzene. So there's the structure of benzene. It's a six-membered ring with alternating single and double bonds. The formula is C6H6. And if you can't see that, then you should try drawing out all of the individual carbons and hydrogens on benzene. So benzene has, well, it's part of a class of a ton of different molecules called aromatic compounds, and essentially the vast majority of those aromatic compounds are derivatives of benzene. So benzene with various things attached at multiple positions. It's found in crude oil, and so because of that, it's found in gasoline. I think the legal maximum is like 0.62% or something like that, but roughly 0.5% component of gasoline. The word benzene is sort of a cognate in some other languages to the word for gasoline. So I always thought that was interesting. And then it used to be a really popular solvent to use in the lab and in industry, but it's carcinogenic. So instead we use toluene, which is just methyl benzene, and it has a lot of the same properties as regular benzene, but it doesn't give you cancer. Hmm? Yeah, it's got a CH3 group, just CH3 on benzene. The other advantage is that the boiling point of benzene is 60 something. It's in the 60s. And the boiling point of toluene is 110. And so generally speaking, higher boiling solvents are more convenient for use in the lab because if you want a reaction to go faster, you can heat that that solution more before you start refluxing or boiling your mixture. So toluene. Okay. We at some point will draw the other resonance structure of benzene. But first, resonance structures in general. So for some molecules, and most of the sort of normal molecules that we're familiar with, we can use one skeletal structure to describe the bonding. So an example would be maybe an alkene like this. So the double bond is telling us that we have between the two carbons, we have two sigma electrons. That's the sigma bond, the first of the double bond. And we've also got two pi electrons. That's the pi bond or the second part of the double bond. So for this molecule, that's fine. The electrons are in fact between the two carbons. And so that's a satisfactory skeletal structure for this molecule, tetramethyl ethylene. But there's a lot of other molecules where just one structure is not descriptive enough of the whole molecule. So an example of that is this molecule. This is called the, come on, allyl cation. And so we've got this alkene on the left, and then we've got a positively charged carbon on the right. So one thing that will be helpful additionally today is, at least for some carbons, drawing out all of the hydrogen atoms. Which for this molecule is fairly straightforward. Okay, we want all the carbons to have 4 bonds, except the positively charged carbon. And a carbon with a positive or negative charge has 3 bonds to it. And so that means that this carbon on the end with a positive charge has to have 2 hydrogens to give it 3 bonds. Anyway, so, and this is kind of weird and kind of interesting. If we do IR spectroscopy or NMR spectroscopy or all sorts of different things, it's going to show us that all of the carbons, all 3 of these carbons, are sp2 hybridized. And so we know that a carbon that's sp2 hybridized is going to have a double bond to it. Or really, I should say a pi bond. So the middle carbon and the one on the left, that makes sense. They look sp2 hybridized. They have a pi bond between them. But the carbon on the right does not have a pi bond, at least the way we've drawn the molecule, doesn't have a pi bond to it. But we know that experimentally that carbon is sp2 hybridized based on the position of those CH bonds in the IR spectrum, for example. They would be above 3000, showing that it's sp2 hybridized rather than below 3000 if it was sp3 hybridized. This is how we actually use IR in organic chemistry. Anyway. Okay, so this structure is not telling the full story. And so we can't draw just a single regular skeletal structure, at least the way we're used to seeing them. That fully describes the bonding in this molecule. So we're going to draw multiple structures, both of which contribute at least in some way or in some amount to the overall structure. And then we sort of take a mental average. In some cases, we'll actually draw sort of an average. And then we take a mental average of those multiple structures, and that kind of tells us what's going on in the molecule. Okay, so for our allyl cation, the first structure that we've drawn is useful because the 2 leftmost carbons are sp2 hybridized. There's one other resonance structure, and it looks like that. Now, for this particular molecule, it looks like I've just flipped it or rotated it, or looking at it from the other side. This molecule is fairly symmetrical, and so that ends up working. But as you'll see oh, it's the wind. Okay. The door started, there was a ghost moving the door. As you'll see in later examples, what's actually happening here is we're showing electrons in two different places in the molecule. And so if we label our carbons A, B, and C in the first resonance structure, okay, they're in the same order in the second structure. And now you can clearly see that there's different stuff happening in both of these structures. Okay, two new sort of symbols that I have drawn. First is, you'll notice there's a different kind of arrow. And it's a double-headed arrow with one bar, okay? So that indicates that those two molecules are resonance structures of each other. Here it's important to note that this is not a reaction arrow, which of course just has one head. Or, and this is an easier mistake to make, or an equilibrium arrow, which is, showing is multi-directional, but the equilibrium arrow is like two half arrows. I remember when I was in Gen Chem and we were taught how to draw an equilibrium arrow. I didn't like drawing the half arrows. I thought they looked funny. And so I ended up drawing something that looked like that on my exam. And then I was baffled to find that the professor did not like that. And I didn't understand why. This is why, because it actually means something different than an equilibrium arrow. So make sure that you can keep those three different kinds of arrows separate. And then the other thing that I put on this drawing are the brackets. Brackets, not parentheses, not curvy braces, but squarish brackets. And these indicate that the structure is inside the bracket. In this case, there's just two, but there can be multiple. And this is really important. It's indicating that those two structures are describing the same entity. So the same molecule. Because they're on two different ends of an arrow, and all of the arrows that we see previously in chemistry, the reaction arrow and the equilibrium arrow, are showing two different molecules. But these two structures are not two different molecules. They're two ways to draw the same molecule. Okay, so another way to think about that is that molecule is not flipping back and forth between the two structures. So one reason why, an additional reason really, why this is a common misconception is because of the word resonance. Okay, that makes you think, okay, the molecule is resonating between those two forms, right? No, that is not what's happening. And so I want you to get the word resonating out of your vocabulary for resonance structures. Because even more so than resonance, the word resonating implies that flipping back and forth. Rather, the true structure of the allyl cation is a hybrid of those two drawings. And so I'm not going to ask you to draw resonance hybrids because they get really complicated really fast with large molecules. Also, they're really vague. But what it looks like for the allyl cation is this. So you can clearly see the three carbons, right? A, B, and C. And the dotted line that's going from A to B to C, that's the two pi electrons that are in the pi bond. They're not entirely between A and B. They're not entirely between B and C. It's sort of smeared across the whole molecule. It doesn't really matter as long as it's a dotted line. And so additionally, you'll notice I put the positive charge kind of in the middle. And it's, again, intentionally vague because essentially I'm just saying that the electrons are spread out evenly across those three carbons, and the positive charge is spread evenly across throughout the molecule. So kind of a stupid little way to remember this or to think about this is that these two resonance structures at the top, so maybe this one is a donkey and this one's a horse. Then our resonance hybrid is a mule. Okay. So if you see a mule, the real molecule, the true structure is a mule. Okay, that's what we actually have in our flask is a tiny little mule. But if you look at a mule, it's not like Schrodinger's cat, right? It's not going back and forth between a donkey and a horse depending on which millisecond you look at it. Or, all right, you can't take a picture and oh, at that millisecond it was a donkey, right? No, it didn't work like that. A mule is always a mule. It's a hybrid of a donkey and a horse. The example in the textbook used some really obscure hybrid fruit that I didn't even know what it was. So I figured this was a more reasonable example. Unless you don't know the difference between a donkey, a mule, and a horse, which I understand. But they're hybrids. Okay. So additionally, let's look a little bit more at the resonance hybrid. I kind of mentioned this in words, but I should write it down, and that is the pi electrons are split across all three of the carbons. And the positive charge is kind of just on the ion itself. It's not in a very specific spot. Previously, I said that this molecule was symmetrical, and when you looked at the original resonance structures, you were like, no, it's not. But look at the resonance hybrid. That's very symmetrical. That's the reason why we can flip it around and it looks the same, even though it's not actually the same. So those electrons, those pi electrons, we call these delocalized. And I think that word delocalized is pretty appropriate for this situation because we're not showing the electrons being in one specific location. They're just kind of in there somewhere. Again, vagueness is intentional here. However, I'm not going to ask you to, because of that, I'm not going to ask you to draw resonance hybrids. I just want you to have seen kind of what they look like. We are going to draw resonance structures, though. Okay, the main takeaway from this is that the donkey and the horse are the mule is not flipping back and forth between the donkey and the horse. It is an average of the donkey and the horse. So now we're kind of going to break that rule that I just told you because we need to have some sort of method for showing the relationship between the donkey and the horse because they are quite similar. He's related to other animals, I guess. Sorry, this maybe it's going too far in that analogy, but so we need a device to show how those are related. And so to do that, we're going to use curved arrows. And these are just tools we're going to use to draw resonance structures. Actually, more importantly, later in the course, in fact, throughout the entire rest of the course, we're going to use curved arrows in chemical reactions. And we'll use them in that case to show the movement of electrons. So they end up being kind of like a roadmap for a chemical reaction. But the resonance structures, that's not a chemical reaction, right? The resonance arrow is not a forward reaction arrow, and it's also not an equilibrium arrow. So specifically in the context of resonance structures, we're going to use curved arrows only as a bookkeeping device. And so we just pretend that the electrons are moving. Because as we know, the electrons are really spread sort of evenly throughout that part of the molecule. Well, in this case, it's the entire molecule. They aren't actually moving around. So a curved arrow, unsurprisingly, is an arrow that's curved, right? Shocker. And it's got a tail and a head. I should probably note that a curved arrow with just one of the hooks in the head is a different kind of curved arrow. And we're not going to use that, so don't do that. Make sure your arrow has a full head on it. And so, okay, the arrow is going to show the movement of electrons, or at least be a bookkeeping device pretending to show the movement of electrons. And so the tail is going to be the source of the electrons, where the electrons are coming from. And unsurprisingly, the head is going to be the destination, where the electrons are going to. So to draw our allyl cation and its two resonance structures, okay, there's our first one. And we said this was the other resonance structure. So we need to draw, in this case, just one curved arrow that tells us how to get from the first resonance structure to the second one. Again, still bearing in mind that we're just using this as a record-keeping device, and the actual structure is an average. So what do we need to do? Well, the pi electrons start off between A and B, and they end up between B and C. So we need an arrow showing the electrons starting out between A and B and ending up between B and C. So we start the tail of our arrow on the pi bond, and it's going to end up on the bond between B and C. So it's going to look like that. So super important is you have to be really, really precise with these arrows. So I'm going to make a copy of this, and I'm going to draw some bad arrows in pink. Okay, so it's really important that not the middle of the arrow doesn't really matter. It's the head and the tail that have to be exactly in the right place. So in order to show this transformation, you don't want to do that, okay? Because that's showing the electrons starting in the pi bond and ending up on the carbon at the end. Okay, so that one's not good. We don't want to show, and there's a bazillion different wrong arrows you can draw. You don't want to show the electrons starting at the carbon on the end and ending up on the bond. You don't want to show the electrons starting on the bond and ending on this carbon. Ooh. Okay, that's also not adequately accurate. And then maybe even an even bigger sin is the arrow shows the movement of electrons, so it has to start where there's electrons. And so some people might look at this and say, ooh, look at the positive charge. It's moving from C to A, right? So we just do this. Show the positive charge moving. The problem is the positive charge is not electrons. It's the absence of electrons. So generally speaking, arrows are going to move from an area with more electron density, so something that has pi bonds or a lone pair or a negative charge, to somewhere that has less electron density, a positive charge, an atom that doesn't have a full octet, or something like that. Okay. Okay. Fortunately, there's only two rules that apply to drawing curved arrows in resonance structures, other than the rule that you have to be precise with your arrows. The first is that we can never make or break a single bond. And so an extension of that is that the resonance structures have to have the same connectivity, right? If there's an oxygen attached to a carbon in one resonance structure, it has to also be attached to that carbon in another resonance structure. So I'm going to do some bad examples here. Okay, so this is a bad arrow because it's showing the breaking of a single bond. So it's showing that the sigma electrons in that bond at the tail of the arrow are moving over to form a double bond between what used to be the positively charged carbon and the carbon in the middle. And so we can see the result of that with our double bond right there. And then there's two carbons off on the right side of the molecule. And because we've broken a sigma bond, those are completely detached. So we've made two molecules here. So the issue is that these are not resonance structures. In fact, this implies that a chemical reaction has occurred. Okay, because the molecule is splitting apart. That's literally a chemical reaction. Okay, can't make or break a single bond because those two structures will not be resonance structures. That shows a chemical reaction happening. So that rule is most easily followed by only moving electrons that are in lone pairs or in pi bonds. And we'll see an example of that in a moment. Okay, the next rule kind of goes back to when we learned about drawing skeletal structures. And that is never exceed an octet for second row elements. So carbon, oxygen, nitrogen, etc. However, if they have like 6 electrons, that's okay. You can have less than an octet. Okay, so in this structure, the arrow, again, bad arrow here, is showing one of the lone pairs on the oxygen atom. Moving toward the carbon-oxygen bond and presumably forming a double bond, right? Now, that doesn't break the first rule. We're not forming or breaking a sigma bond. But, and this is a case where it's probably good to draw out all of the hydrogens. Okay, there's all our hydrogens. And now we can see that, okay, this carbon in the middle here already has 4 bonds, 1, 2, 3, 4. And so if we try to bring those electrons from the oxygen to make a double bond there, that would give the carbon 10 electrons. That would exceed its octet. And so we can't do that. Now, having less than an octet of electrons is okay. So what I can do is something like this.
Because oxygen can't do that, right? And carbon can't.
So oxygen now has, okay, the oxygen has an octet here in the end, so that's okay. The carbon has 6 electrons, so it has less than an octet. That's actually also okay. And it's got to have a positive charge because it's only got 3 valence electrons. And then the oxygen has a negative charge because it's got 1, 2, 3, 4, 5, 6, 7 valence electrons. So it gets a negative charge. For this, you probably want to go back to your see the chart of like the carbon, nitrogen, oxygen, fluorine with various numbers of bonds and lone pairs, or just practice assigning formal charges in that way.
In the second structure, why aren't we drawing a curved arrow going back to where that double bond was? It's not a single bond.
Like this? That's okay. And so generally, I'll just ask you to show it going in one direction. But you can also draw that arrow to show that to go the other direction, you would draw that arrow going down. So that's not a bad thing to do. Although one thing to remember is that the arrow is a set of instructions that haven't yet been carried out. Okay, so in the absence of this structure, just looking at that, you couldn't say, "Ooh, okay, well, those electrons are moving away from the carbon, so the carbon has a positive charge and the oxygen has a negative charge." No, because you should be able to erase the arrow and still have a correct structure. So we've kind of already shown an example of that here, but let's show the process for predicting the results of some curved arrows. Okay, so there's what we're going to do. You can have multiple curved arrows at once. That's legal. So the first step that you should do is draw all the atoms and all the sigma bonds, because those don't change when we draw resonance structures. So this is like a skeletal structure with just single bonds. Then, continuing with this what's staying the same business, we'll draw the pi electrons and lone pairs that don't move. Okay, so those are going to be all of the pi electrons and lone pairs that don't have an arrow making them do something. So the oxygen has got two lone pairs, one on the top and one on the left. The lone pair on the left is going to do something. It's going to come down and make a double bond. The pi electrons in the double bond down here are going to do something. They're going to scoot onto the carbon atom. But the lone pair on the top of the oxygen doesn't do anything. So we'll leave that in place. No pi bonds to transfer over because we have one pi bond and it's busy. Okay, the big step is we actually have to draw the result of the arrows. So this is just going to have to do with electrons that do move. Okay. So this is one place where you should kind of just turn your brain off and take everything literally. So the lone pair on the left of the oxygen is going to come down and it's drawn toward that sigma bond between the oxygen and the carbon. So that's going to make a double bond. And then the pi electrons that were in the original pi bond, the carbon-carbon pi bond, are, and you see how that arrow is drawn from the pi bond to the carbon atom, the vertex of that joint right there. So that's going to have those electrons moving onto the carbon as a lone pair. You notice we really have two different types of actions happening. We have a lone pair becoming a pi bond and a pi bond becoming a lone pair. It's common for those two to happen together. Okay, so we've carried out the instructions, and now all we have to do is add formal charges, because a structure without formal charges is always, well, a structure that is missing formal charges is always wrong, always wrong. So here you could consult your little table, but what atom has a positive charge? Oxygen. 3 bonds and 1 lone pair. And what atom has a negative charge? Yeah, the carbon with the lone pair. So an easy, well, I don't know about easy, but a mnemonic for remembering this is that generally speaking, sorry, electrons. No, that's not how I want to say this. It's phrased kind of weirdly. To phrase that strangely. No, that's okay, I guess. So electrons are moving away from the oxygen, right? And so oxygen is going to end up with a positive charge. Electrons are moving toward that carbon, the one that ends up with the negative charge. And so that carbon ends up having a negative charge. I think that makes sense, right? Because electrons are negatively charged. So if the electrons are moving toward an atom and end up there, that atom is going to be more negatively charged than it was previously. And the opposite is true for where the electrons started out. The electrons have gone away from the oxygen. And so the oxygen is now electron deficient, which means it has a positive charge. Now, this isn't to say that every time you see an arrow being drawn that takes electrons away from something, that it's automatically going to get a positive charge. But it's never going to get a negative charge if that kind of thing happens. All right, so generally speaking, electrons are moving southeast here, and our negative charge is going to end up kind of on the southeast part of the molecule. It's a very hand-wavy thing, but it works. Okay, so I mentioned how we have the lone pair making a pi bond and the pi bond making a lone pair. We can extend that significantly. And we can extend that to some really common patterns that we often see when drawing resonance structures. And in fact, if you can reliably reproduce these 5 patterns, you can basically do any resonance structure. We'll go over the first couple of them today. The first is an allylic lone pair. So we need a definition here of allylic. By the way, it does have to do with the allyl cation that we talked about at the beginning. So the allylic positions are any atom, doesn't have to be a carbon, any element that is right next to a carbon in a carbon-carbon double bond. So next to alkene. Okay, the 2 carbons that are in the alkene are not allylic, but those 4 things that are attached, they can be hydrogens or carbons or an oxygen or whatever. But those are the allylic positions. Okay, so if we have a lone pair, that means we've got an allylic, if we have an allylic lone pair, that means that one of those atoms at the allylic position has got a lone pair. So I really hate this molecule that I chose, but it's a good example. Okay, there we go. So in this molecule, well, there's our double bond, our carbon-carbon double bond. And if we have an allylic lone pair, that means it's a lone pair on an atom that is attached to one of the carbons in the carbon-carbon double bond. Okay, so here's the 2 carbons in the carbon-carbon double bond. Actually, let me do that in a different color. So there's our carbons, the CC double bond. So that means our allylic positions are there. So that carbon in the northeast corner, no lone pair there, we don't care about it. But our nitrogen at the bottom here is allylic. So that lone pair is allylic. But the one on the top is not an allylic lone pair. I'm gonna get rid of the gold. Oh, yes, got it. Okay. So what does an allylic lone pair do, or what can it do? Well, it can come around and turn into a pi bond. And then the pi electrons can move on to that carbon. So this is the exact same thing we just did in the last example. No, it doesn't look like it. But that last example was an allylic lone pair. So results of this. Okay, what do we do? First, we draw all the atoms and all the sigma bonds. Okay, so atom, 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 sigma bond, sigma bond. Okay, that's all the atoms and all the sigma bonds. Then we draw the pi electrons and lone pairs that don't move. Okay, so the lone pair at the bottom is moving. That pi bond is moving, but the lone pair on the top nitrogen is not moving. So we can draw that in. So that's not changing. Then we draw the results of the arrows. Okay, so our lone pair is moving to that sigma bond, and so that's going to create a pi bond right there between the nitrogen and the carbon. And then the pi electrons from the pi bond, the original pi bond, are moving on to this carbon atom. And then we just assign formal charges. So this is what we can use our kind of mnemonic method where, okay, in this case, the electrons are kind of moving northeast. So we would expect the northeast bit to be more negatively charged and the southwest bit to be more positively charged. So the electrons are ending up on the carbon. We said that that was where the electrons were headed. Okay, yep, carbon with 3 bonds. One of them's to hydrogen and it's not drawn. But with a lone pair, that's a negative charge. And then a nitrogen with 4 bonds and no lone pair, yep, that's a positive charge. Questions on that, specifically on the arrows? That's the most important part.
How know we're moving to that direction again?
How do you know when we need to do what?
We know where the arrows need to go.
We're going to talk about that a little bit more next time.
Okay.
You kind of, for that, you kind of have to know what a good ending resonance structure looks like, and then draw the arrows that show the formation of that. So what we've been doing in these examples is I've given you some arrows and told you to carry out the instructions. But another thing that we'll talk about doing eventually at some point is this. I'll give you this and say, okay, draw me the arrows. Okay, and so that's, you're sort of doing it backwards. Actually, that's a little bit easier, honestly, but we'll do that as well. All right. Cool. See you on Monday.